Okay, we will continue now with Chapter 28, working on magnetic field sources. And here we will look at some simple geometries and compute what the magnetic field is for these geometries. Let me move this paper up just a little, so I have more room to work. And we're on here, section 28.2, the magnetic field for simple geometries. Well, you have to use some pretty difficult and time-consuming calculus in order to compute these. So I'm just going to present the results, and that's what we need for a course at this level. Once you have both calculus and advanced calculus, one can compute these as is done in a more difficult physics course. And just with a little bit of thought, you can go back to those original equations we had for the magnetic field and see how each infinitesimal piece contributes and do those integrals. But for now, we just have to memorize the results. We want the magnetic field at a distance a from an infinite straight wire. So we're going to imagine an infinitely long wire. That way we don't have any end effects, and we have a current I that's flowing in this infinitely long straight wire. And it turns out that you can use the right-hand rule to compute what the magnetic field is. The magnetic field goes around this wire in a circle where your thumb goes in the direction of the current and your fingers go around the wire as if you're grasping them, go around the wire exactly as the magnetic field would. So if this is the wire we're talking about, then I'm saying put your thumb in the direction of the current and your fingers go around just like the magnetic field would, under the wire and over the top. And the magnetic field is given by B is equal to mu naught I over 2 pi A. Now, you may remember an analogy to this, and the analogy was if I have a lot of charge, of lambda charge per unit length, that we had an equation likewise for the electric field due to an infinitely long straight wire. And that equation was E is equal to lambda over 2 pi epsilon radius or distance away from the wire there. Whereas A is the distance away from the wire here, we could have equally written an R there. And except for this mu naught always being in the opposite position from epsilon naught, this equation here is identical to this equation here. So this is our new equation. This tells us what the magnetic field is due to an infinitely long wire. You can say, well, I don't know what this is. Well, I can multiply by 2 and get a mu naught over 4 pi. So let's imagine, for example, we were trying to find it a distance of 4 meters away from a wire that had 7 amps in it. Then our magnetic field B would very simply be mu naught over 4 pi, now so I multiply the denominator by 2, so I'll multiply this by 2, over 2I over A. This is 1e to the 7th, to the minus 7th, you recall. And therefore, this I is going to be multiplied by 2 here. So we have 2 times 7 is 14, divided by the distance, and the distance is going to be 4. So the answer is the magnetic field out here is going to be 14 over 4 e to the minus 7th at a distance of 4 meters away. So that tells us how to do a computation for an infinitely long straight wire. And again, I point out in the notes we can compare that to lambda over 2 pi epsilon naught r, this equation here, which gives us the electric field due to an infinitely long straight wire. Once we learn things for the electric field, the magnetic field simulates that to a great extent. Of course, the current I replaces the charge density, and you'll notice that both of them have a 1 over R dependence. I used A instead of R here, but we could have put an R right here, and it looks very much like that. It's a 1 over R, not 1 over R squared. The next equation we want to look at is the field on an axis, a distance from a circular loop with a current I and a radius R. So here, what we have is a circular loop. We're going to look along the axis. This has a radius R. And we're going to go up on this axis. I use a capital R here. We're going to go up a distance x and say, if we have a current I that's flowing around here, it's a radius R, what is the magnetic field at this point? That's up a distance x from the center of the circle where the current is flowing. And the answer again is B is equal to mu naught I R squared divided by 2x squared plus R squared to the 3/2. Kind of a messy formula. And sometimes I require that students learn this formula, and sometimes they do not, depending upon the level of the course. In a harder course, one has to actually derive this by integrating the angles here of how each of these currents contributes to a magnetic field that points out in different directions and, of course, averages up to be in that direction there. What direction would that magnetic field be? Well, if I grab this loop here, I can see that I would grab the loop with my thumb pointing in that direction, and my fingers would go upward. That means the field is going to be upward at each point, so the part that goes away from the axis cancels on each side, and so I have a magnetic field in the upward direction away from that loop. So the magnetic field goes like this through that loop. And that's in general true. In fact, if I have a loop here that's in the plane and I have a current I that goes around it, the magnetic field comes up through that loop and goes out. That's the B field. And that is exactly like if I were to take my thumb along part of this loop here and let my fingers come up through the loop. That's the way you always find, using that right-hand rule, what the magnetic field direction is. And I'm going to look at a solenoid, and a solenoid is where I have tons of different loops. And of course the current goes out here and it comes in here. And I can say, okay, if I have N, which is the total number of turns divided by the length, and this would be the length. This is number of turns per unit length here. Then the magnetic field that exists inside this loop, or to draw field B that's inside this loop, as the loop goes around, again, depending upon how those turns are done exactly, you would point this way or that way, depending upon the current. And the equation for that is B is equal to mu naught N times I, which is the current. Mu naught again times the amount of current that's flowing, however much current I is flowing, times the number of turns per unit length. Number of turns per unit length. So I'm going to write here again that this is equal to total number of turns divided by the length of the wire. So we have three new equations. This one to tell us inside a solenoid, this one for a loop of wire along the axis, and this one away from an infinitely long straight wire. 1, 2, 3 different equations, new equations for how to find the magnetic field. Of course, these are all based on the Biot-Savart law, which gives us the infinitesimal magnetic field due to an infinitesimal piece of wire.